السلام عليكم وكل عام وأنتم بخير. وحقيقة I'm so delighted إنه we are back again in these weekly sessions. Starting from this Saturday, I think as of this Saturday, we are going to continue regularly every Saturday as we used to. And we are going to gear up to the intermediate module of cardiology. And I'm going to circulate the schedule soon. I have taken into account all your suggestions, okay? It will be as you are expecting, inshallah. This is just reactivation session, and next session will be with Dr. Abdul Majid. I think it will be about heart failure. For tonight, we are going to discuss M-mode in echocardiography. And to start with, if we go to the historical background of echo, the very first technology in echo was probably the M-mode, okay? It was earlier than the 2D and the Doppler. And you see the images on the left. These are the initial M-mode images obtained from a patient by the use of echo technology back in 1953, okay? Are we still using M-mode or it's just historical? يعني نحن we have to be pragmatic when we are utilizing any technology. It's not about academic interest and historical sentimentality. It's about the utility, the actual utility of M-mode. But is M-mode actually still beneficial or is just superseded by the rest of echo modalities? And I'm waiting for your answer. So you think M-mode still has a place in echo? Mm-hmm. Anybody? Did you hear me?
Yeah, yes. Still, you can use it and it's helpful.
Okay. So you think it's still helpful, right? Okay. So
Yeah.
that will bring us to the characteristic of the M-mode, because when we say it's helpful, we have to tell why. Because the M-mode historically, like we said, was the initial modality of echo. Then there is the 2D, the Doppler, the 3D, and now the strain. Okay. So if M-mode is still has a place in echo study, so that place must be occupied fair and square due to special characteristic of the M-mode. So let's take this MCQs. Which statement is right about M-mode echo? It is supplanted by the newer modes. It has the best temporal resolution compared to 2D and 3D. It gives no additional information. M-mode drive chamber measurements are insensitive to alignment.
B. إجابة B.
B. Okay, that's good. Yeah. So I think that is right. So M-mode still has a place and is still useful, and still sometimes, occasionally, can even be the type of data where you kind of fall back on to diagnose subtle abnormalities, especially in the motion of the valve and the chamber motion and stuff like that. And we are going to explain all of that. And so this M-mode did not fall yet because of its best temporal resolution compared to all other echo modes. So the temporal resolution of the M-mode is the best among the rest of the modes. يعني أحسن من ال 2D, definitely أحسن من ال 3D, definitely أحسن من ال TDI. يعني let's just to compare the temporal resolution of the M-mode is 1800 frame per second, okay? While the 2D is like 30 frames per second. So it's a big difference, you know? And this temporal resolution meaning what? Meaning a sampling rate is high. Sampling rate is high. So it can capture so many like events in the cardiac cycle. That's why when these data is stretched kind of linearly in that linear structure or linear format of the M-mode, you could see very subtle changes in the motion of the valve and wall that you cannot pick from the 2D. يعني الآن الموشن, if we take this one for example, just look at the mitral valve M mode, the one on the bottom left, E, A, C, and D. When you look at the same mitral valve in the 2D, you are hard to appreciate that the valve goes opening, approach to close, and open again. You don't see that because the temporal resolution of 2D is not as good as M mode. Okay, so the M mode allows you to pick up the detailed timing and structures taking place in the cardiac cycle. Okay. Now, what are we using M mode for? We are using M mode for the walls, by which we measure the interventricular septal thickness, posterior wall thickness. We are calculating dimensions, in systolic dimension, in diastolic dimension. We are doing TAPSI. We are interrogating the IVC in terms of collapsibility, spirophysically, and in terms of diameter by M mode. We also do mitral valve M mode to see the E&E. We do aortic valve M mode to see the excursion during systole and diastole. And we interrogate the septum sometimes if you are suspecting constriction for paradoxical bouncing, shatter, and all of this subtle motion of the septum. We also see the RV free wall. If in case of tamponade and pericardial effusion, we look for RV diastolic collapse. And there are still others. Okay, so routinely, any echo study should include M mode for the walls, for dimension, for TAPSI, for IVC, and one snapshot of mitral valve and aortic valve. You agree? That's any routine echo study, especially dimension, TAPSI, IVC, mitral valve, and aortic valve. So if we take this one, the routine use of M mode in echo covers all the following aspects except. لاحظ هنا the routine use of echo. Routine use of echo, the one we are doing like regularly and on day-to-day basis. TAPSI, MAPSI, fractional shortening, mitral valve M mode, aortic valve, and root M mode. Which one we are not doing routinely?
B.
The
MAPSI,
right? Yes. MAPSI,
B.
we don't use it routinely. MAPSI stands for mitral annular plane systolic excursion, and TAPSI stands for tricuspid annular plane systolic excursion. TAPSI is routine for RV systolic evaluation. Fractional shortening is kind of routine in systolic and in diastolic dimension of the RV and of the LV, sorry. Mitral M mode, aortic valve, and aortic root M mode is kind of routine. MAPSI is not used unless for any special circumstances, and basically it's more of academic rather than practical. Now, these are the routine M mode, which we find in the majority of echo done routinely. We find the M mode of the mitral, M mode of the aortic, and M mode for dimensions and systolic and diastolic dimension calculation, TAPSI, and IVC, right? This is the routine M mode echo. So it's kind of 1, 2, 3, 4, 5, 6 images of M mode likely to be found in the routine echo study. The problem with the M mode is that you see your lines, these lines, the one shown in 2D. These lines are important. You have to drop them perpendicular because the accuracy of your alignment to be perpendicular will reflect in the accuracy of the measurement. So if you go oblique, then you are gonna undercall or overcall the dimension. So you have to make sure that your alignment is set at right angle. This is important, okay? Now, if we look at the aortic, the mitral valve M mode, that's how it looks like. We have E, A, C, and D. E stands for the initial opening, A for the atrial contraction, C for closure, D for the opening, and F for the slope from E down to F. They call it EF slope. Okay. Now, when you see here the dimensions, we have the end diastolic dimension and end systolic dimension. This is how they are measured. Remember, they are measured from the inner wall to the inner wall to the inner wall, like the one done here. And from this one, you can derive the fractional shortening. The fractional shortening is the end diastolic dimension minus the end systolic dimension over the end diastolic dimension. Okay, so it looks like we are calculating the stroke volume, but in 2-dimensional instead of 3-dimensional. Okay, now the TAPC is the RV free wall at the base, and this is how you obtain and how you calculate it. The IVC from the subcostal, and this is the M mode, and you can measure, by the M mode, you can measure the dimension of the IVC, and you can see better than 2D if it's collapsible during respiration or not. So this is the fractional shortening equation. It's the LVN diastolic dimension minus LVN systolic dimension over LVN diastolic dimension. Okay. Okay. So the normal is 25. In some other references, they put it 28 to 40. That's the normal, 28 to 40%. But more than 25 is kind of normal. Okay, more than 25 is normal. And then in between, like moderate lower than 15% is severe impairment. Now my question is, how is the accuracy of fractional shortening in the calculation of systolic or reflecting the systolic function of the LV? What do you think about it?
I think it's sensitive because it depends on how the septum and posterior wall getting thick and go back again to their previous status.
Anna, what I mean is, do you think it's a good surrogate of the ejection fraction, good surrogate of the systolic contraction, systolic performance if you use the fractional shortening?
No.
Why? Okay.
Because it depends on the segment that you made the M mode on again across it.
Thank you so much. That is exactly the right answer. So the fractional shortening is not good in the LV because the LV might be regionally problematic. It's not necessarily global. Yes. In case of yes, exactly. In case of global hypokinesis, fractional shortening might be accurate. But in segmental wall motion abnormality, fractional shortening, because you are sampling one dimension, that one dimension might not reflect the rest of the myocardium. So you might be misled. Now, if I take the same fractional shortening for, let's say, for the RV, will you see, would you still have the same impression about it in the RV? fractional area shortening, and TAPC. TAPC is also a single dimension analysis, right? Single dimension analysis reflecting the entire RV function. Now, MAPC, which is again a single dimension analysis, is kind of obsolete. Nobody is using it for the LV because the LV might be regionally abnormal. The other thing is that we have better measurement for the LV systolic function than this single dimension analysis. So now for RV, why are we still using fractional shortening and we are still using TAPC? While in LV, we have advanced in using complex ways of measurement. The answer lies in two. One is the RV actually, that's what we get. Yeah, the LV is easy to study, easy to put in mathematical modeling and stuff like that. So you can do the Simpson and. It's difficult in the RV given the complex geometry and all of that. So out of desperation, we have used this single analysis, single dimension analysis. The other thing about the RV is that in the vast majority of problems that inflict the RV, when the RV goes weak, it goes weak globally. It's not like the LV. And even in ischemia, myocardial infarction, RV infarction, how does the RV behave in RV infarction? It goes weak globally, not segmented. So if you use single dimension in the RV, it might be enough. It's not like in the LV. Okay. So these are probably the two reasons why we are still using single dimension analysis in the RV. Okay. So remember this fractional shortening. And now, the fractional shortening is an accurate as ejection fraction in LV systolic function evaluation. And you probably said no. It reflects the longitudinal movement of the heart. The longitudinal movement of the heart. The longitudinal movement of the heart is based on LV dimension measured from leading edge to leading edge. All is false, all is true. All is false or all is true or is based on LV dimension measured from leading to leading, reflects the longitudinal movement of the heart. طبعا we said that it's as accurate as ejection fraction. This is wrong. It's not as accurate as ejection fraction. Okay. So number A or A is wrong. Now what about B? It reflects the longitudinal movement of the heart.
Wrong.
Wrong. It reflects what kind of movement of the heart?
The circular one.
Yes, the circular, which is called radial.
Yeah.
Okay, the radial movement, which is kind from yani, it's the lateral from out to in, from out to in. Longitudinal meaning from up down, That's the longitudinal. And from up down is reflected by MAPC and TAPC. MAPC and TAPC are more or less longitudinal plane movement. Okay, so it is radial movement, not longitudinal movement. Now, how are we doing it? We said from inner edge to inner edge, right? From the inner edge to the inner edge. Now, if I take this one here,
This is
this one here, if I take this one, this is the inner to the inner. You see my line? The red line?
Yes.
So this is inner to inner. What if this, if I do it like that, this will be what? I do it like that. This is called what? And if I do it like that, what is it called? And if I do it like that, what is it called? Believe it or not, the first time I go for National Board of Echo USA, I find these measurements and they want to ask about a very fussy question about the terminologies of echo, leading edge, trailing edge, leading and trailing. This part is called the leading. The wall, the front of the wall, this part is called the leading. This part is called trailing. Leading means in front. Trailing means behind. Leading, trailing. So the first line, which is here, is from where? It's from trailing edge to leading edge. Trailing edge to leading edge, right? Right? It's from the trailing edge of one wall to the leading edge of the opposing wall. Agree?
Yes.
Now the second line, which is here, the second line is from leading edge of one wall to the leading edge of the second wall. This is wrong. You shouldn't do it this way. Now the third one is from trailing edge to trailing edge. This is
Yes.
wrong. The last one is from leading edge to trailing edge. This is wrong. So the right way of measurement is from trailing edge to leading edge. That's what they want you to answer, to select this one, trailing to leading edge. Trailing to leading edge, in another easier, simplistic way, is inner edge to inner edge. Inner edge
Yes.
to inner edge, meaning
Yes.
trailing to leading. Okay? But sometimes they just complicate things for you. So, sorry, let's erase this one. Okay. So now the answer here will be from leading edge to leading edge is wrong, longitudinal wrong because radial, so all is false here, right? Good. Now, let's see the mitral valve M mode. In the mitral valve M mode, you have to observe how much the mitral valve opens in systolic. This is one thing. How the valve closes, how the valve opens in diastole, how it closes in systole, and how much it opens, how much it opens. And how much it opens, there are some ways of objective evaluation, but I'm not needed so much recently because, you know, we are using some other more accurate measurement. But the most important part is this part. This part. Sorry. You see this one? So the distance from the peak, the distance from the peak of E to the septum. So that is called EPSS, E point to septal separation. So this E point to septal separation distance can reflect the cardiac output, the stroke volume, and the LV systolic function indirectly, right? Because if the heart is weak, it will fail to open the mitral valve enough. So that distance will lengthen. So the more of distance between the peak of E and the septum, the weaker the heart. You agree? Okay.
Yes.
So this is important. Now this is the normal M mode of the aortic valve. So it's usually described as rectangular, abrupt opening and abrupt closure. See this terminology, abrupt opening and abrupt closure. Because if the closure is gradual, the opening is gradual, and in the middle there is not sure mid-systolic closure, that's all abnormal. Okay? Then this line is also important, the closure line in diastole. The closure line is important. You look at it if it's in the center or if it's eccentric, because in bicuspid tends to be more of eccentric closure rather than central closure. Okay, so this is how the normal M mode of the mitral valve looks like. Okay, so keep it in mind because we are going to contrast this one with abnormal signals shortly. Okay. Now, this M mode, now we are taking abnormal M modes after we have seen the normal M mode of the mitral valve. This M mode is best described as reverberation artifact, mitral stenosis, mitral valve mass, reverberation artifact, and mitral stenosis. So whoever can take this one. Don't be embarrassed to speak your mind out, whatever it is. Don't worry at all. So what do you think this M mode is describing? Reverberation artifact, mitral stenosis, mitral valve mass, or both reverberation artifact and mitral stenosis?
D.
D. Can you explain?
Yeah, if we see the box in diastolic, it looks to me, anterior leaflet, it looks a little bit thicker.
Yes, very good.
So this is maybe it goes with mitral rheumatic stenosis.
Very good.
But if we see a systole, you feel like posterior leaflet prolapse, and it's not obvious to me, and not sure.
Yes, I agree with you so much, Muhammad. Most of that is right. You see the valve here. This valve, if you look at it, it is thickened. And you feel that in the middle, there is something. That is calcium. And this calcium is not the true calcium. Is not the true calcium. This is calcium magnified by reverberation artifact. Because we know from the technology of echo, which uses ultrasound, whenever the ultrasound beam hits an echo dense surface, it might reverberate, so it bounces back and forth, so it multiplies the images. Okay. So now what we are seeing here is calcium multiplied by reverberation artifact. And you see this part here. What is this part here? This blackishness here. This is shadow artifact. So that is exactly what we see. Reverberation artifact, whenever the ultrasound hits the beam, hits an echo dense area, so it gets magnified. And behind that one, the ultrasound is concealed, so did not penetrate down there, so you will see an acoustic shadow behind. So that's an acoustic shadow. So this is a calcified rheumatic mitral valve with mitral stenosis and reverberation artifact. Can we tell about the severity of mitral stenosis from this one? Definitely no. Definitely no. Okay. Yes, you might have an impression, but no kind of precise quantification can be drawn out of this. Okay. Okay. So now, next, look at this one here. These are two patients with rheumatic mitral valve. The one on the left, the one on the right. Which one you think is more severely stenotic valve? Which one is more severely stenotic valve?
The first one.
Yes, I agree with you. The first one, because it's more thickening, and the width.
The one of the left.
Yes, exactly, the one on the left. Because the width, the thickening is clearly more on the left side, and there is reverberation artifact, not as pronounced as the case we had shown just before. الحاجة الثانية الموجودة لو لاحظتوا السبيس between the leaflet is a bit tighter on the left than on the right. Okay, لأنه in the rheumatic valve the anterior leaflet moves forward. I mean, it opens. The posterior wall, the posterior movement is pulled towards it instead of the usual excursion when the posterior leaflet goes away from the anterior leaflet in diastole. Now the anterior mitral leaflet is dominant. It moves forward and pulls the posterior leaflet with it. That's why you see here this part. This part here. Okay, you see here, usually the posterior, if you take this, it goes like that. So the posterior leaflet moves away from the anterior leaflet. But if you have rheumatic, it goes like that. The posterior tends to go towards the anterior leaflet. Tends to go towards the anterior leaflet. Okay? So this is a manifestation of rheumatic morphology, rheumatic anatomy, and it's clear. But again, we cannot quantify the degree of stenosis from M-mode. Okay. So this M-mode suggests an artifact, myxoma, vegetation, stenosis, prolapse.
Myxoma?
Myxoma.
Myxoma, okay.
Yes, protruding to the valve.
Yes. Why not vegetation?
Because it filled the whole time of the diastolic.
Yeah.
Okay.
If a difference between the myxoma and vegetation here is kind of, I cannot be so sure. Yes, it's more likely to be myxoma, but it may be vegetation, right? Yes, it's more likely. That's why we say suggest. Yes, it's more suggest. Because the myxoma usually fills the entire space between the leaflet, like in the vegetation tends to be small and occupy a certain space, not the full space between the two leaflets. But that is kind of, not hard and fast rules, because you might have a myxoma is small and you might have vegetation that is big enough. Okay? Like in the tendency to fill in the space between the leaflets is more of myxoma than vegetation. The vegetation looks more or less like this one, the one on the left. You see this one? The one on the left. The one on the left, you see the space between the two leaflets is not fully occupied by this echo-dense mass. So this is more likely vegetation. While the one on the right, you see the mass is kind of filling all the space between the two leaflets. That is more of myxoma. Okay. So this measurement, and we talked about that, reflects fractional shortening, LA diameter, E wave height, LV systolic function, TAM.
E wave height.
E wave height.
ES.
Yes, that is EPSS. EPSS. Okay. So that reflects what then from these options?
LV systolic function.
Yeah, exactly. EPSS. E point septal separation distance. Okay. So this is reflects the LV systolic function. In what way it reflects the LV systolic function? In this way. If it is less than 8, that is normal. More than 8, that's abnormal. Then if it's more than 10, it's significantly abnormal and stuff like that. But usually the cutoff threshold is 8. It has to be lesser than 8 because we said that the shorter this distance, meaning the stronger the mitral valve opens. And if it's strongly opening, meaning the cardiac output, it is enough. لكن لما يكون في low cardiac output, the leaflet hardly opens, so the leaflet is not pushed far further closer to the septum, and the distance tends to be long. So more than 8 is abnormal, less than 8 is normal. Okay. Right. Now, this arrow points to. Try to find out this arrow first. See where this arrow pointing to. Normal mitral valve excursion, alignment artifact, premature closure, premature opening, or V-pump.
We didn't see the arrow.
The arrow is here. I will show it to
Where is the arrow?
you. You see this part, okay? So it's like, if I draw it schematically, like
a B pump.
Yes, B bump.
exactly.
People.
So you see the anterior leaflet, instead of having E and A, there is another shared small subtle wave at the closure, before the closure. They call it AC shoulder. This one is A and this is C, right? We accepted that this A and this is C, A and C. So this is called AC shoulder. So we have an opening or a wave in AC shoulder that tends to open the valve. So the valve in AC shoulder is closing. Now we have a wave that interrupts that closure. This is the B pump. And the P pump signifies what?
High ADP.
High EDP.
Diastolic dysfunction.
Yes. Okay. Good. It signifies high LVEDP, and there are so many theories as to the exact mechanism of the P pump and how it reflects high LVEDP, something kind of complex. Okay. Now, what is this? Now, remember the M modes of the aortic valve I have shown you. Compare that to what we are seeing now.
The exit closure.
This is mid-systolic closure. Mid-systolic closure. Exactly. So you see here, that is mid-systolic closure. If you check this one, you see the valve goes up and then it closes and then it opens again. So it's kind of like, okay. So it looks more or less like mitral is the aortic valve. Okay. So what's the meaning of this mid-systolic notch?
Yes.
This mid-systolic notch signifies or indicates or is in keeping with or consistent with. Anybody?
Yeah, it signifies.
Yes.
Severe.
Sorry? Sorry, I missed your answer.
Severe LV systolic dysfunction.
Severe LV systolic dysfunction. I might accept that, but if you look again, yeah, I know why you made this confusion. But this one is sharply a mid-systolic closure. Mid-systolic closure after which the valve opens again.
Sometimes not with the dynamic LVOT.
Exactly. This is dynamic LVOT obstruction. This is HOOCM. Okay? And because HOOCM leads to mid-systolic flow acceleration, mid-systolic flow acceleration, mid-systolic flow acceleration dagger-shaped signal means what? Whenever the velocity of the flow increases, the pressure drops. When the pressure drops, the valve tends to close. And then in late systole, it opens again. So that's the mechanism of LV or T obstruction in M mode. It leads to mid-systolic notch. Mid-systolic notch is HOOCM. Mid-systolic notch is HOOCM. Okay? Good. So now you understand it. So the equivalency, the Doppler equivalency of this notch is the dagger-shaped signal. Because in the dagger-shaped signal, what we see simply is this one.
Gradient. Yes.
Yeah, we are seeing this one. So if you check here, the velocity here is much faster than the first half of the signal. The first half of the signal is a slow velocity. The mid half of the signal is fast velocity. Fast velocity means what? The pressure here is how much? Tell me about the pressure in the initial signal, the pressure. High pressure. Because the velocity and the pressure are inversely proportional. Yeah, the higher the velocity, the lower the pressure. So here the pressure is high, while in the second half of the signal, the pressure is low. And that is why the leaflet tends to close, because the pressure below the valve is tending to be low. The valve tends to close and then it opens again. Okay? So if you take things together, you can make a better understanding of the physiology of cardiac physiology. Okay, this is good. Now move on. Now what is this? What is true about TAP-C? It is a validated way of RV systolic function assessment. 15 millimeter marks the threshold of normal. It always reflects the entire RV function. It's not affected by TV bioprocesses. So what do you think?
A.
A. A. Sorry, who said A?
14 is B.
B. 14. Okay, so
C.
Umayma said 14. Right.
C.
Who said A, validated when?
Me, Muhammad.
Oh, Muhammad, right. Okay, and I think Muhammad is right. If we take B, 14, no, it is 16, 17, but now we say 17. 17, above 17. Below
Yes,
17 is abnormal, okay?
Yes.
It always reflects the entire RV function. Here we have to say no, not because it's always, but because we remember, we said, if you remember, that the TAP-C is a single dimension analysis, assuming that this single dimension reflects the entire RV. And this holds true for the vast majority of RV problems, but not always. يعني الآن مثال بسيط. If you have, let's say, مثلا pulmonary embolism. Pulmonary embolism tends to create this McConnell sign, right? In the McConnell sign, you tend to have what? You have to tend hyperkinetic effects, while the RV free wall is hypokinetic. So there is segmentation in the functionality of the RV. Okay? In Takotsubo, the apex tends to be hypokinetic. Okay? The free wall is fine. So again, there is regionality. So RV is not always going weak systematically. Sometimes it goes weak regionally. Okay? So that's not right. So the right answer is, it's a validated way of RV systolic function assessment. Now, the RV tricuspid bioprosthesis is an even repair will splint the annulus. So the annulus will be splinted, okay? It will be adherent, tight. So the excursion of the annulus no longer normal to express the RV systolic function. So if you have bioprosthesis, if you have repair, you cannot like
نعم على كيفك عايل اسهل لك بس بشوف اقرب الو
yes. So you get my point here. The bioprosthesis and the tricuspid repair will affect the accuracy of the TAP-C, okay, by means of what it does on the leaflet in terms of adherence to the cardiac skeleton, and it becomes kind of not stretchable as it used to be. Okay, so far so good. Guys, are you following me?
Yeah, very nice.
Good, good. Now,
Yes, we're doing.
The MAP-C, we said the MAP-C is again taken from the lateral mitral annulus, okay? And this is the MAP-C. My question is, do you think the MAP-C, the normal MAP-C, is equal to the normal TAP-C? lesser than or more than?
Lesser.
Without asking you about the figure. Thank you so much. It's lesser. The base of the heart contracts more vigorously on the right side than on the left side. The RV is more longitudinally deformable than the LV. I agree with you. Yes. Okay. So the MAPC is lower. Now, we said that the MAPC is no longer used for LV systolic function assessment because simply we have the problem of regionality in the LV, which is more prominent than in the RV. And because we also have so many more objective and more accurate ways of assessing LV function. Good. Now, this image on the left is consistent with septal excursion of constriction. It is more specific than RA collapse for tamponade. Its degree does not change with respiration. It indicates large precordial effusion. I will show you here. Look close. What am I showing you? What am I showing you? Back to the question. Septal excursion of constriction, more specific than RA collapse for tamponade, does not change with respiration, indicates large precordial effusion.
Consistent with septal excursion of constriction.
Is it constriction?
بقول be more specific for RA collapse for tamponade.
Yes. It's more pronounced. The RV collapse is more pronounced. I'm zooming in. You see this one, the diastolic RV collapse or RV inversion during early diastole. You see it here. This one, I can point to that. Just give me time here. This one here. That's the collapse. Okay. That's the diastolic inversion of the RV. Okay. This diastolic inversion of the RV is abnormal. Okay. Because during diastole, the RV tends to stretch out. In fact, it's inverted inward here because of the pressure from the precordial effusion. Okay. So this is a sign of, let's go back to the question and pick up the right answer. Okay. Go here. So which one you are going to choose? Indicates septal excursion of constriction, that's out. More specific than RA collapse, does not change with respiration, indicates large precordial effusion. Come on, D, if you choose D, I will be mad at you. Because we know that it's not about the volume as much as about the speed of accumulation. The speed of the accumulation is so deterministic in the tamponade physiology, probably much more than the volume. Okay, so it can be small and tamponading, can be moderate and tamponading. So it's not necessarily large precordial effusion. So we have A and D, which are out. What else?
More specific than RA collapse.
Exactly. That is right. It's more specific than RA collapse for tamponade. Now,
Dr. Hatim, can I ask a question, please? Can you comment on anterior and posterior septal movement?
Anterior and posterior septal movement. Okay. This one you mean? You mean the posterior leaflet here? This is the posterior leaflet. And here, of course, the mitral valve with the posterior wall.
Sorry, Dr. Hatim. No, posterior wall. if we see, if you calculate number 1, 2, 3, 4, in 5 beat, the posterior wall is going in systole, going inside, while the posterior septal is going out.
Yes, yes,
Well,
you're right.
actually, it's
Yes,
a
you're right.
paradoxical
And this is
movement.
exactly, that is so important. Yeah, yeah. That's the other finding in this tracing is that the septal is paradoxical because during systole, as we see here, the septum is bulging out. So this is paradoxical septal motion, which again is a sign of restraining from outside. The heart is restrained from outside, either constriction or tamponade. Yeah. So I agree with you. Yeah, I agree with you. Okay. Now, my question is back here. If I take you back, what about it does not, its degree does not change with respiration? We have to think about this one because this MCQ is not so accurate.
It looks like a pericardial constriction. It changes respiration.
Yes. Okay. Good. So look at here. This is from Bone Echocardiography, 6th edition. Look at what he showed us. This is RV diastolic collapse. But if you follow it down the different beats, you see sometimes it becomes more prominent and then it disappears. What's the meaning of that? It changes, meaning that the RV diastolic collapse has also manifested respiratory variation. By the way, the entire RV, I mean the tamponade physiology, is respirophasic dependent. It depends on the stage of respiration, even the RV diastolic collapse. Because during any expiration, the volume of the blood in the RV is low, so it's more amenable to pressure from outside. So during expiration, you see this RV diastolic collapse more than you see it during inspiration. Yeah, you get the point. So it is again respirophasic. Even the RV diastolic collapse is respirophasic. Okay. Good. Now, this is again a very pronounced example of the RV diastolic collapse. Now, the RV diastolic collapse takes place at what time of the cardiac cycle? What time of the cardiac cycle?
Question, please, again, Dr. Har.
Sorry? The question is, the diastolic RV collapse takes place at which stage of the cardiac cycle?
Diastole.
Yes. And what stage of diastole? Early, mid, or late?
Early diastole.
Exactly. Why?
At the closure of the aortic valve.
Okay. Good. So I think we can discuss this along with the RA inversion. Now the RA and the RV both will be compressed by the large precardial effusion or by the tamponading precardial effusion to be accurate. Now, at what time of the cardiac cycle will the RV get compressed? We have to think of it physiologically. Now, the RV is more vulnerable to be compressed from outside when its pressure is the lowest. The pressure is the lowest in the RV in early diastole. In early diastole, it's the lowest. Okay? Now, the RA is compressed maximally when the pressure inside the RA is the lowest. And it's the lowest in late diastole. Late diastole. Okay? So the RV gets compressed in late diastole because its pressure is low. the RV gets compressed in early diastole because its pressure during that phase is the lowest. Okay? You get the point?
Yes.
Okay. Now look at the RA. We talk about specificity and sensitivity, and I know so many of you has done so many echoes. And whenever you find large, moderate, small, sometimes precardial effusion, before you can demonstrate the RV diastolic collapse, you're most likely going to demonstrate the RA collapse. So the RA collapse takes place much earlier than the RV collapse. That's why it is sensitive but not specific, meaning what? You can have small non-tamponading precardial effusion, but you see that the RA is inverted. Okay? So the RA is sensitive but not specific, meaning what? If the patient is tamponading, you must demonstrate RA collapse. But if the patient is having RA inversion, she does not necessarily have tamponade. You get the point? That's what it is. لكن الRV inversion is different. RA inversion has a very positive predictive value of tamponade. If you see it, the patient most likely is tamponadic. Okay, so it's specific. Now, look at this one. This is a mode of the RA wall. A mode of the RA wall. You see, a mode of the RA wall. We don't do it a lot, but we have done it here because the M mode provides us with the best frame rate, so we can see the extension of the wall and we can time it against the cardiac cycle. We cannot do that in 2D, but we can do it here. Now look at the time of the wall inversion here, this one. This part, sorry. This is inversion. It's supposed to be like that. The wall goes like that. Now we see that the wall goes in. Okay? So it goes in. I will take this time of going in against the cardiac cycle. How much of the cardiac cycle that inversion is taking place? How long is occupying of the cardiac cycle? If it occupies more than 30% of the cardiac cycle, it becomes specific of tamponade. So we cannot dismiss the RA inversion as non-specific. Yes, it is sensitive, but not specific. But if you quantify it in terms of timing, how much of time the RA is inverted against the time of the cardiac cycle, and if we demonstrate that this time is more than 30% of the cardiac cycle, then we are specifically talking about tamponade. Okay? So this is important piece of information because it has been asked frequently and people fail to answer right because we are so mind oriented towards the RV inversion and we dismiss the RA inversion. RA inversion is still diagnostic of tamponade if we quantify in terms of time. Okay? So remember this one. Good? Are you following?
Yeah.
Okay, now what it is, sorry, what is true about IVC and IVC-M mode? It reflects the RA pressure in all clinical circumstances. It leads to false collapse due to abdominal wall movement. It is interrogated for systolic reversal in TR. It is interrogated for diastolic reversal in constriction. Mm-hmm.
It leads to false collapse due to abdominal wall motion.
Okay, so you have selected the right answer. Exactly. So it reflects the RA pressure in all clinical circumstances. Usually the the IVC reflects the RA pressure. And that's why we are using it. That's what we use it for. But not always. Not always. لأنه مثلا الآن if you, let's say if you have an obstruction of the IVC anywhere between the right atrium and the liver, it will stop translating the RA pressure, right? Right? If lymph node, tumor, whatever, encroaching upon the IVC, closing, obstructing it, therefore it no longer reflects the RA pressure because that continuous column of pressure between the RA and the IVC no longer exists. So not in all clinical circumstances. Now, interrogated for systolic reversal in TR, no, but routinely and conventionally, we interrogate the hepatic vein for systolic reversal in TR and for diastolic reversal in constriction, not the IVC. So the right answer is B. And B is very important information I wish you all know about. لأنه في أحيان كثيرة while you are interrogating the IVC, the abdominal wall moves up and down, so your probe gets up and down, and you kind of, the image kind of disappears and comes again. When it disappears and come again, the tracing will connect to each other. When it disappears, you feel that if there was like 100% collapsibility. And when it comes again, you see that it is open, the IVC is open, and when it disappears, the IVC is closed, and therefore you tend to say that I have great collapsibility. While there is no collapsibility, in fact, what you have is the image has come in and out of your probe, has come in and out of your imaging capture. So you sometimes capture it, you sometimes lose it. When you lose it, you think that the IVC has collapsed 100%, but you lose it because the abdominal wall has moved, your probe has moved. So, and the abdominal subcostal window is always tough to image in because with the respiratory motion of the abdomen, we tend to have the image quality going up and down. So you have to ask the patient to hold his breathing for some time and then to sniff and keep firmly pressing in the window so as not to lose it. Okay. So this is the IVC, and this is how we calculate the RA pressure. The RA pressure on the last column is calculated in terms of IVC size and the degree of collapsibility, and that's how we do it. It's kind of crude way of assessment. It's not so accurate, but that's what any kind of rule of thumb, and it has been validated invasively, and it's reasonably doing well in terms of pulmonary artery systolic pressure assessment. So the pulmonary artery systolic assessment needs two signals: the TR signal on one side and the IVC on the other side. That's what we usually have, right? طبعا قد تكونوا لاحظتوا انه في مشاكل كثيره بتحصل لناس echocardiologists when they are asked to evaluate the pulmonary artery systolic pressure, and we give a figure. The patient goes invasively and they get a different figure. So an invasive hemodynamics is supposed to be more accurate. Okay. We have to apologize because we have two signals we are using in pulmonary artery systolic pressure assessment, both of which has its own caveat. يعني TR signal ممكن تكون poor quality. إذا عندك severe TR, you tend to have low velocity. Okay. IVC, you know, the collapsibility and how much you are going to add, 5, 10, 15, it's kind of crude estimation. So يعني the method by which we are calculating pulmonary artery systolic pressure by echo is not so accurate. لذلك we tend to apologize when we get invasive figure telling us that our measurement is not so accurate. We know it's not accurate. It's not accurate. Okay? So don't feel so proud of the pulmonary artery systolic pressure in echo. Always remember there are so many limitations. The IVC is one, and the quality of the signal and the velocity of the signal of PR on the other side. So now what is this? This M mode shows and reflects anterior mitral leaflet flutter, which is the sign of severe AR, anterior mitral leaflet flutter, which is the sign of severe MR, mitral valve premature closure, which is the sign of severe LV systolic dysfunction, the echo equivalent of Austin Flint murmur. So, which one you think is right?
A.
A.
I will go with D.
I think it is C. C. Premature closure is a sign of severe LV dysfunction.
Okay. Good.
D, I think.
It's a bit tough because they tend to be kind of really correct with a small, problem with each one of them. Now, C tends to be right until the time when it tells about, when you look at it, we know that the mitral valve, when it closes prematurely, it's a sign of LV systolic dysfunction. It opens weakly and closes prematurely. Yeah, this is a sign of severe LV systolic dysfunction. But if you look at this M mode, there is another sign. There are two signs. One is
fluttering of anterior mitral leaflet.
Exactly.
With the AR.
Yes. So we have two things here. We have fluttering of the anterior leaflet and we have premature closure. Okay. So together, they mean something else. So not C. So
it's an A.
An A. Okay. A. A also
not indicate severe AR.
Okay.
It can happen also with mild to moderate AR. It's not sign of severity.
Good. So the flutter itself is not a sign of severe AR. I agree with you. The flutter is not a sign of severe AR. The flutter, remember, because this is an area of dispute, the flutter itself is not a sign of severe AR. It's a sign of a jet of AR that comes into the mitral, into the anterior mitral leaflet. So it indicates the direction rather than the severity. You can have severe AR that gets behind or away from the mitral valve and no flutter. And you can have mild moderate AR that comes right into the anterior leaflet and causes it to flutter. So it's a matter of direction rather than volume. What indicates severity is how much the AR closes the mitral valve. How much the AR closes the mitral valve. That means severity. لكن السؤال والناس بيفتكروا أنه the closure of the mitral valve when you have severe AR is caused by what? What causes the premature closure of the mitral valve when you have severe AR?
High diastolic volume.
Thank you so much. So it's
video.
not, yes, it's not about that volume from the LVOT going into the direction of the mitral leaflet, impeding it to open up fully. No, it's because the LVEDP will be tremendously high, so it tends to equalize the diastolic pressure between the LA and LV quickly and prematurely, and therefore the flow stops to go from up down. So that's why it leads to premature closure because of the high LVEDP. Okay? So the premature closure is so meaningful in terms of AR quantification. The flutter itself indicates direction, not severity. So if we go back to this one here, therefore A will be wrong, B is definitely wrong, C is wrong, it's the equivalent of Austin Flint murmur. What we are seeing here is a sign of severe AR. Why did we say AR? I just knew that this patient is having AR because of the flutter. And I knew that this patient had, sorry, again, I will rephrase. I knew this patient is having AR because of the flutter. But I knew it is severe because of the premature closure. So the answer in this question is that I have severe AR. And severe AR leading to premature closure, which can be picked by clinical exam as Austin Flint murmur. Austin Flint murmur is a murmur of functional mitral stenosis as a result of severe AR. Okay, so D is the right answer. And this is again a better image of the premature closure and the flutter. The flutter can tell you just about AR is there, but the premature closure tells you about severity. Okay? So far, so fine? Okay? Are you okay so far?
Yeah.
Yes, we're okay.
Good. Yeah. I think there is a time lag between in the sound or something, or my sound is clear.
That is clear, but
No, it's clear.
we are waiting for somebody to respond.
Okay. Right. The M mode is suggestive. This M mode is suggestive. We have seen this one, so you can pick the right answer right away without further explanation. What do you see here? You see this one? It's now clear. Mid-systolic notch of the aortic valve. This is what? Yes.
C.
C. It's dynamic
yeah.
LVOT. Exactly. Dynamic LVOT obstruction. Believe it or not, there are so good portion of examining who has chosen E. Has chosen E, normal M mode of the mitral valve. See, the mitral valve does not reside in this box of the aortic root. You have to remember, even if you don't see the 2D, you can figure out where is this structure, where this structure is, right? This must be aortic valve. Huh?
مقلوب ولا شنو؟
Yeah, في بعض الناس يفتكروا انه this one is the mitral valve. This one, because E, A, C, and D, the same expression of the mitral valve, so they have chosen E.
But if they are looking to the castle, like actually in the aortic valve.
Exactly. Yes. Mahi, sometimes, you know, in the heat of the moment of the exam, you get lost sometimes and you feel like you're stressed out, you don't think properly. And you feel that's so easy, let's just choose E and move on. You know, يعني لكن أنا بقول إيش إنه even if you are not provided with 2D, you can still say إنه, or you can still know this is the aorta, not the mitral, you know, because the aortic root is clear. This one is the aortic root, so you can know these chambers are RV, aortic root, and left atrium. You know exactly the arrangement of the structure in this linear data. Okay. Again, this is just the same patient. Now, this is a bit tough. Okay, and honestly speaking, when I have seen it the first time, I didn't know the right answer. And I was taken aback when I knew the right answer. Whenever I show it anywhere, nobody gets the right answer. So don't worry. This is, we can just describe it here. What we are seeing is the aortic valve, right? Right? We are seeing the aortic valve. So if you can describe it right, I might be so happy and glad.
Okay. In the area of the aorta, we have aortic valve outflow obstruction. With gradually opening.
Okay.
They're returning to the normal. In
yes.
compared with the heart cycle, we have about 2 to 3 heart cycles without opening of the aortic valve.
Oh, great, great, almost, yeah. So we have 3 systoles did not open the aortic valve. What's the meaning of this?
This means we have an outflow tract obstruction.
If you have an outflow tract obstruction, you will have it beat specific. So each beat, there is an obstruction. Why it becomes like phasic? You have it, then you don't have it for some time, then you have it again for some time.
Fixed obstruction.
If you have fixed obstruction, you tend to have each beat is showing the same manifestation. If it's dynamic, like LVOT obstruction, you again should have the notching and should be appearing each and every systole. But in this case, we fail to find.
What about the ECG?
The ECG is fine. Look, yeah, this is good idea to look at the ECG when the aortic valve is not there. There might be kind of pause. Yeah, I might accept that, but no pauses. There is electrical activity, but the aortic valve is not opening during this time. Okay, so this one actually was a case of tamponade, and this is pulsus paradoxus. Extreme form of pulsus paradoxus. Usually in pulsus paradoxus, during expiration, during inspiration, the blood pools on the right side and the septum shift leftward. So you have decreased cardiac output on the right side, on the left side. The cardiac output will decrease on the left side during inspiration in tamponade. You agree? Yes, it decreases. So how much it decreases? Usually 10% decrease. But now this is too much decrease to the extent of having no appreciable cardiac output enough to open the valve. This one, when the valve was closed, this is inspiration. Then during expiration, the stroke volume improves and the blood flows back again and opens the valve again. And again, during inspiration, it closes again. Okay? So this is pulsus paradoxus. Okay? You can see it in M mode. Usually, you could appreciate a subtler form of pulsus paradoxus by M mode, like during inspiration, you will see that the valve still opens, but to a smaller degree than during expiration, but not disappearing completely like this one. Okay, so this is extreme form of tamponade and extreme form of pulsus paradox. I think I will not hold you more than that. There are some remaining for the M mode. We might catch up on that later. But so far, I think we have covered the vast majority. The rest of the presentation will be about practical application and about the imposition of M mode with color, and how we can interpret both of them. So we can leave that for next session, inshallah. Tamam?